Okay, so this time we're going to look at a Charles Law problem. It says a gas that is initially at 23 degrees Celsius is heated to 78 degrees Celsius. If the initial volume is 1.40 liters, what is the final volume, assuming or if the pressure remains constant? Okay. So Charles's law relates volume and temperature. So if we write PV over NT, Charles's law relates volume and temperature. So we're doing V1 over T1 equals V2 over T2. And we have a lot of this information already in the problem as well. So the gas that is initially at 23 degrees Celsius, that's our T1 value, our initial temperature, is heated to 78 degrees Celsius. So that would be our T2 value. If the initial volume is 1.4, so that would be our V1, our initial volume, what is the final volume? So we are looking for V2 in this problem. Okay, so now that we've labeled our variables, let's go ahead and get them written out. So our V1 is 1.40 liters. Our V2, we don't know. We are looking for that variable. Our T1 is 23 degrees Celsius, but when we use Charles's law, we want to always convert our temperature to Kelvin. And this is because gas laws are not made to deal with negative temperatures. If you have a negative temperature, the gas law will not work. You won't be able to solve your equation properly. And so the Kelvin scale was actually invented so that our gas laws would work. So we never would end up with a temperature below 0 on the Kelvin scale, because 0 on the Kelvin scale is absolute 0, meaning the absolute lowest theoretically possible temperature. So for this problem, leaving the temperature in Celsius won't make a difference because both of our temperatures are positive. But if we ever have a negative temperature, the gas law won't work and you will get the wrong answer. So just out of good practice, we're going to practice converting the temperatures to Kelvin every single time we do this. So our T1 value, we can convert that to Kelvin just by adding 273. So 23 plus 273 is 296 Kelvin. And then 78 plus 273 is 351 Kelvin. And so now we have both of our temperatures in Kelvin. All that's left is to substitute into our equation. So V1, 1.40 liters, over T1, 296 Kelvin, equals V2, which we don't know, so we're going to substitute in X, over T2, which is 351 Kelvin. So now this is a case where we probably want to cross multiply. So we're going to do 1.4 times 351, 1.4 times 351 equals 296 times X. So now I'm going to move our work up here. We'll go ahead and do some math. So let's do, let's see, 351 times 1.4. So that gives us 491.4 equals 296 times X. And of course we need to move the 296 to the other side. So we'll divide by 296, divide by 296, and we end up with X equals 491.4 divided by 296. So X equals 1.6601. But of course, we need to round our answer to the appropriate number of significant figures. Looking back at our problem, we have 3 significant figures, 2 significant figures, and 2. So we'll round our answer to 1.7. Our X was equal to our V2, so V2 equals 1.7. Last but not least, we need to look at our units of volume, which are liters. 1.7 liters. And that is our final answer.